Although we have been working for quite a while with finding limits numerically and then checking our work using the graph of the function, sometimes we don't have a formula for the function. We need to be able to determine the limits of a function if we are only given its graph. So for example, let's look at this crazy function here. We've got a bunch of limits and function values to determine. Let's first look at the limit as x approaches 3 of the function f of x. I'd highly encourage you to pause this video and try and see if you can determine what each of these limit values are, and then unpause it and check your work after you try your hand at this. To determine this, first note that it is a two-sided limit. If we look at the function with x equals 3, what we're going to do is kind of march along the function in both directions and let x approach 3, and see what's happening to the y values. Do they look like they're heading towards something? At x equals 3, there's no problem with the graph. There's no jump, there's no hole, there's no asymptote. And so in this situation, the limit is just the function value, which if we kind of estimate from the graph, that looks like it's approximately 2. Below that, we have the limit as x approaches -1. This is also a two-sided limit. If we locate -1 on the x-axis, there's also nothing strange going on in the graph at x equals -1. This is the point on the graph right there. There's no holes, there's no jumps, there's no vertical asymptotes. And when that's the case, the limit is just the point. It looks like it's heading towards this point here on the x-axis when x is -1 from both directions, and it actually does hit that point, although that doesn't matter for the limit. Now the y value on the x-axis, the height, you're not going up or down, so that y value there is equal to 0. In the third one here, we have the limit as x approaches 0 from both sides. X approaching 0 is right here on the y-axis. So if we go along the function and we look at what's happening at x equals 0 or x approaching 0, again, nothing strange is happening. We can just read off the function value there, which is 2. Right, where it looks like it's heading and where it looks like it's heading both directions here, it actually does attain that value. But again, that doesn't matter for limits, but it does look like it's heading towards a y value of 2. These three cases are what happens when direct substitution works. When you can just plug in the value that you're finding the limit at, and you don't get 0 over 0 or a non-zero number over 0. You just have a nice situation. The curve has a point there, and you can just read that off by substituting in the value. If we move to the right, in the set of limits right here, they are all looking at what's happening at x approaching -4. The first one is x approaching -4, but from the left-hand side. So let's take a look at the graph. Here is x equals -4, and we're looking along the function as x approaches -4 from the left. Now there is a hole in the graph at x equals -4, but remember with the limit, it doesn't matter what happens at x equals -4, we can actually just cover that up. What does it look like the function's heading towards? What is the y value that it should be if we didn't know any better that there was a hole there? And that location here looks like it's at a y value of 1. So this limit value will be +1. The second limit underneath that, we have x approaching -4, but from the right-hand side. So it's the same place here, but now we're going along the function from the other direction. And we do have this hole here, but cover that up and try and figure out what it looks like the function's heading towards as you approach -4 from the right. And again, that looks like you should have a y value of 1 there. The third limit is the two-sided limit as x approaches -4. Now remember that a two-sided limit exists if the individual sides or the individual one-sided limits go to the same place. Here, they're pinching towards the same point. We also wrote down that the limit from the left and the right, they were both equal to 1. When that's the case, the two-sided limit exists and is equal to the value of the individual one-sided limits. The last one here, f of -4, this is actually not a limit. This is the function value at x equals -4. So if we're trying to find that, we're looking at what happens when you plug in -4 into the function. Well, we have this open circle here, and there's no point above or below -4 that's filled in anywhere. So that indicates that the function, again, is undefined, when you plug in x equals -4. So we can write that f of -4 is undefined, or even that that does not exist. Now, this situation is sort of what happens when you have a hole in the graph. And also, this is what happens when you substitute in direct substitution and you get 0/0 out. We'll talk more about this when we work on our algebraic techniques for finding limits, but just as a preview, we want to connect all these things together. So when you have a hole like this, the two-sided limits, the two one-sided limits match up. The two-sided limit exists, but you have an undefined function value. That usually happens when you have 0/0 when you try to substitute in your x value. The next set, down at the bottom left, is looking at what happens as x approaches 2. So if we look at what's happening on the graph at x equals 2, we see that there is a jump. So this might be indicated by a piecewise function if we had a formula for it. But we don't need to know, again, a formula. We're just trying to estimate this by looking at the graph. So the first one is the limit as x approaches 2 from the left. So we're going to be approaching 2, but from the left side. So we cover up what happens at 2, and we just kind of look. If I only knew that we were going towards 2 and heading on the graph right along this curve, then it looks like I should be heading towards a y value of 3 when I get to 2. So that means that we would say that the limit here is equal to 2. Underneath that, we have x approaching 2 from the right side this time. So that means we're going to be going along the function. Again, we'll cover up what happens at 2. We're going to be following this part of the curve. And if we didn't know any better, we only had this information as we approach 2 from the right, it looks like that we should be heading towards this point here, which has a y value of 1. The next one here is a two-sided limit as x approaches 2 from both sides. In the next set of examples down here, we are looking at what happens around x equals 2. The first one we're looking as x approaches 2 from the left. So here's 2 on the graph. We see that there's something interesting happening here. There's a jump. Maybe this is indicated by a piecewise function if we were to have a formula for it. The first one from the left-hand side means that we're going to be marching along the function from the left with numbers less than 2. And again, we can cover up what happens at 2. And we're just trying to answer the question, what does it look like the y values are heading towards as we approach 2 from the left? And of course, it looks like we should be heading towards this y value of 3. So that is the value of that limit. On the other hand, from the right-hand side, we look like we're doing something different. So let's go along the function here. We'll cover up what happens at 2, and we'll come along this part of the function from the right-hand side. Now it looks like that the y values here are approaching something different. Right, we have a 1 that it looks like we should be heading towards. So the right-sided limit or the right-handed limit as you approach 2 should be 1. Now this third one here is the two-sided limit as x approaches 2. Now remember that when you have the one-sided limits that don't match up, or you have a disagreement about where the function's heading towards from the left and the right, or this jump in the graph, then we say that the two-sided limit does not exist, or DNE for short. Now, just to make it clear, we can have a two-sided limit existing if there is a hole in the graph, because we could have a situation like at -4, where the limits from each side kind of are in agreement. It looks like they're pinching towards the same spot. But when we have this break or jump in the graph, that's a different story. Their expectations about what's going to happen as x gets closer and closer to 2 aren't in agreement. And that is when we say that the two-sided limit does not exist. Lastly, here we have the function value f of 2. So here we are only concerned with what happens when x equals 2. So we're not going to look at x approaching 2. We're just going to say look up directly up at 2, or maybe directly down, and see where's there a filled in point. And of course, you can see that there's a filled in point right here. This is our open circle. So the filled in function value, or what happens at x equals 2, filled in point, will be the value of 3. In our last set of questions here, we are investigating what's happening as x approaches -2. The first one is x approaching -2 from the left. Okay, so here's -2. We see that at -2, this dashed line indicates that we have a vertical asymptote. So we have unbounded behavior, which means probably one of our limits isn't going to exist. But if we look at x approaching -2 from the left, that means we're going along the function from this direction. This behavior is unbounded. This arrow means that the function will continue going up and up and up, and just keep on going up, and it will never cross this vertical asymptote at x equals -2. So because we're going up, the y values will be increasing, and this limit here will be positive infinity in that case. On the other side, as x approaches -2 from the right, we have the function going down. Again, this arrow indicates the same thing, that the function's going down, 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 and the y values here will become more and more negative, or will approach negative infinity. The two-sided limit, as x approaches -2, because we've got this disconnect and they're kind of doing different things, they're definitely not going towards the same point. Here we say that this also is DNE, or does not exist. Lastly, the function value at -2. What do we get when we plug in -2 into the function? Well, we can't. There is no point on the graph. There's no point filled in. Just like this hole here, there's no solid point above or below -2. So this one is undefined. And we will talk more about this, but this situation is what happens when direct substitution gives you a not zero in the numerator and then a zero in the denominator. You'll have a vertical asymptote with this unbounded behavior, possibly infinity or negative infinity, or maybe a two-sided limit that doesn't exist.